Yeah, it's on.
Can you hear this? This seems to be loud. Is this loud enough? Shall I say some more? I think it's okay like this. Yeah, this. Okay, works. Maybe too loud even. It's a bit loud, no? Okay. This is, yeah. Now I don't hear it.
Right now the room is empty, so you want to put off? Off, on, off.
Probando, probando. 1, 2. Bueno, para nuestros asistentes virtuales vamos a tratar de emitir con la mejor calidad posible del sonido. Nos disculpan si tenemos dificultades técnicas en ese sentido. Bueno, buenas tardes a todos. y bienvenidos a el segundo encuentro del AstroTwinCoLO, que es el programa de instituciones hermanas entre la Universidad de Leiden y la Universidad de Antioquia. Ahora voy a hacer el switch a inglés para, digamos, que demos honor al hecho de que todos los cursos se van a realizar en esa lengua. Okay, so we are really pleased to have here a Professor Konrad Kuiken. my first attempt. Maybe you can give us a couple of slides about how to pronounce the last name, and Huygens. Maybe Huygens is also. So we are really pleased to have the Professor Konrad here at the University of Antioquia in this intensive course regarding gravitational lensing, which is his specialty. You can see the curriculum vitae of Professor Konrad in the website of the meeting, and also you can see over there all the information regarding the course, the content, and all the material that will be produced during this week. We have given you these 2 pages, which are very important for us. These 2 pages are a copy of the email I sent you yesterday to all your accounts, and here you will find all the URLs or the web web addresses important for the courses, including especially the schedule of the courses that can be found in the official web page, the page of the live stream emission, the live stream broadcasting. You can follow these courses online. Right now we have a couple of people connected with the course. And for those who are following the course virtually, you can present the tests of the courses following the last page I refer in this document. Again, for people following the course virtually, this document will be available in our website this afternoon. Okay, very fastly, just to give allow Professor Konrad to start. The dynamic of the course is very simple. We have 2 sessions each day from now to Friday. Each day you will have half an hour test regarding the content of the last day. For those tests, Professor Konrad will give you a couple of exercises to perform during the rest of the day and the morning after today. So we are asking all your commitment with the course. You have to be very, very careful this week, because we just have 1 week with Professor Konrad to cover all the content of the course. So any question, if you have any question regarding the course, regarding all the organization issues of the meeting, please write me to my email any question you have. Okay? So, Professor Konrad, thank you very much to be with us. Enjoy this week.
Can you hear me? Does this work? So, I know that I'm going to enjoy this week. I hope you're going to enjoy this week too. The subject of the course that I'm going to give this week is gravitational lensing, which is a phenomenon which in astronomy has been talked about for more than 50 years, but has only really become important in the last 20 years. And so what I will try to do in this week is give you an overview of what lensing really is, and then the various scenarios in which we, in astronomy, in research, actually use it to measure things, to learn more about the universe. This is a course which I've given in Leiden before. In Leiden I do it in 8 weeks, and here I do it in 4 days. So I've tried to take some of the material out, but nonetheless, many of the things, normally it's nice to have a few days to think about something. Here you will not have the time to think about things quite so much. So I hope it's going to work. What I'm going to do today is start with a kind of overview of qualitatively describing what lensing is and where we see it. And then in the second half we will move into the fundamentals of lensing, which is going to be a lot of mathematics, tracing light rays, seeing how they are affected by gravity, doing some optics with them. And then the next few days we will go more towards the applications in the various scenarios that I will. So let's start with a little bit about the course. There's going to be a total of 4 days. Every day we'll have 2 sessions. This is the introduction and the basic concepts which we're going to do today. And then tomorrow we will spend the time on strong lensing, which is the situation where light from a distant quasar, for example, is split into various images by an intervening lens. The day after we will talk about microlensing, which is gravitational lensing in our own galaxy, so not on cosmological scales, but much closer to home. And then the last day will be on weak lensing, which is really the frontier of gravitational lensing at the moment, where we're trying to do a lot of cosmology and also preparing for important satellite missions like the Euclid mission and the WFIRST mission, which are going to do this on an enormous scale. As Jorge already explained, every day I will, most days I will give you some homework at the end of the day to work on, and then the following day there will be a test on the material. That's not going to be the homework itself, but it will be questions which you can answer very easily if you've done the homework. And there are questions which you have not done the homework, you will have difficulty to answer. So do the homework. The homework is not the test in itself, but it's the preparation for the test for the following day. This course is based on material from a course in the Swiss Alps in Saas-Fee in 2003. There's a very nice book from that which really has everything in lensing, much more than we're going to cover this week. But I've put links to the various chapters which are all online and freely available on the course website. And it's divided in 4 books which will follow these 4 chapters. So in each time I will give you, each of these is about 100 pages or more, so I'm not going to ask you to read all that, so I'll give you, I'll recommend certain sections for you to read to prepare for the lectures, to try to keep on following the material. Okay, so let's start about gravitational lensing. For who here is the concept of gravitational lensing completely new, and who knows a little bit about this? For who is it new? 1. Everybody else knows about gravitational lensing, then I can go home. That's great. So the idea of lensing is very simply, it's the phenomenon is that light rays are affected by gravitational fields. We're always taught in school that light travels in a straight line. That's true if you define the straight line correctly, and the straight lines in the real world have to take account of gravitational fields. So light, if you like, falls under gravity just like particles do, just like a football does. When you kick it up, it comes down again. The same goes for photons, for light particles. They feel gravitational fields, and their orbits are changed by them. And the proper way to describe all this is using general relativity, which describes how particles move in curved space-time and how you get these phenomena. I'm not going to use general relativity in this course at all, except for one. I'm going to reduce all of general relativity to a factor of 2, which I will introduce with a magic wand when we get to it, so don't worry about GR. But everything that I'm going to say can be derived properly using the equations of Einstein, of course. Instead, what we're going to do is use the theory of Newton, which is a lot simpler, and simply think of light as particles that travel with the speed of light. So it's like I shoot particles at the speed of light, and I see how they are affected by gravitational fields. And then the trick is that to go from these Newtonian calculations to Einstein, you simply multiply all the deflections by a factor of 2. That's all there is to it. And so, even though you can do this properly with relativity, I'm going to do this Newton times 2 description to keep things simple. Whenever.
Any question you want to do, please with this mic, just because we have people in the internet. You can ask questions in English and Spanish. Okay, so don't be shy. Just ask questions.
My big question is, where does the factor 2 come from? Very surprising.
I will tell you this.
Do they formally use a factor 2?
I will come to this later. I won't prove it, but I will show you where it comes from. In the back.
Gracias, profesor. Para la partícula en gravedad de Newton, ¿qué masa utilizan para calcular el ángulo de rectángulo?
The mass doesn't matter. It's a test particle.
¿Por qué?
It's the equivalence principle. If I throw a heavy ball or a light ball in the air, they all follow the same orbit, right? So the mass of the particle, of the test particle, doesn't matter. What matters is the mass of the lens that's doing the bending.
Pero la luz no tiene más.
Yeah, but those have the same mass.
Light is no mass.
The mass is, yeah, well,
Which might be used to...
your problem is that the mass is zero, you think? Or,
Yeah.
okay, well, we're going to pretend that it's not quite zero. And in fact, a photon has a little bit of energy, which in relativity corresponds to some mass. I mean, look, I'm cheating, right? I'm using Newtonian theory for something for which it doesn't really apply. It's just a way to get through all of it. Yeah? So we're going to describe this mathematically later, but this is in principle what happens. If you imagine a heavy mass like the Earth or a star or whatever, and you shoot particles past it, then these particles will get deflected by the gravitational field. The closer they get, the stronger the deflection will be. And you can do this for particles that move at any speed. In particular, you can do this for particles that move at speed c. And we're going to see later that this bending angle is inversely proportional to the distance that you come to the mass. If you stay twice as far away, your bending angle becomes twice as low. And so you see, just like in normal lensing, this is a kind of focusing effect, right? Light rays that started off parallel end up moving towards each other and are being focused in some sense. And typically, the kind of angles that we will meet in astronomy and cosmology are of the orders of arc seconds or arc minutes. So these are really very tiny angles. This is very exaggerated the way I've drawn this. So all the angles in this whole course are always going to be very small, which means I'm always going to be using the small angle approximation, right? So I'm not even going to say that most of the time, but I'm going to say that the angles are so small that whether I take the sine or the tangent, it's just the same as the angle itself. Okay, so this is the picture of lensing that you have to have in mind, and we will describe this mathematically later. Now, if you compare this to the lenses that you're used to, right, this is a gravitational lens, this is a normal optical lens that you use in a camera or something, then you see a big difference. Right? In this case, the bending angle gets smaller and smaller and smaller as you get further away from the lens, whereas in the kind of lenses that you're used to, the bending angle gets bigger and bigger and bigger as you get further away from the lens. The lens works harder and harder the further you get away, which is not how gravity works. It's not how gravitational lenses work. This lens has to do this so that it puts everything in a nice focus. The gravitational lens doesn't do this. The gravitational lens does not make a nice single focus. There's a technical term. A gravitational lens is what we know as a bad lens. This is a good lens. A gravitational lens is a bad lens. It doesn't make a focus. So see that these light rays come to a focus here, these light rays focus further away, these ones focus even further. You get a very complicated behavior. And so nonetheless, we can work with this as lenses, but much of the intuition that you have from normal optics that you may have played with in the laboratory, for example, it will be different here because the lenses behave in a different way. So what we do in astronomy, when we are dealing with the gravitational lenses, here we are looking at the sky. We see light rays that are coming towards us from a certain direction, and what we don't know necessarily is that these light rays have been deflected, have been bent at some point through lensing. And so, because we're looking in this direction, we think that this source here is somewhere over there in the sky. It seems to come from there, the light, so the source is somewhere up there. But in fact, if this lens had not been here to deflect these light rays nicely towards us, then if this lens had not been here, then in fact we would have seen the source in this direction. So this is a schematic illustration that shows that what gravitational lenses do is they move around the positions of objects on the sky as long as the objects are lying behind the lens. Right? So if there's a massive object here, everything behind it is moved to a different position because all the light rays that we see have somehow had a bump, been bent by this effect. And if you think about this a little bit more, then you see that almost always what happens is that the image is kind of pushed away from the lens. So this source was actually very close to the lens on the sky. Right? These are almost in the same direction, but what we see, the image that we see, is actually further away from the lens than it would have been otherwise. So even though this is kind of counterintuitive, but even though gravitation is an attractive force, it pulls things towards it. In gravitational lensing, it's the opposite. In gravitational lenses push images away from massive objects in the sky. And the reason why you get this inverse is because we are tracing the light rays backwards. So things which the gravitational lens, what it does is it kind of pushes the sky around it away a little bit. And we will see many examples of this as we go through the week. And so if you know how strong this lens is, if you know how strong it bends light rays wherever you go, then it's always very easy to work backwards, to start a light ray that you see, trace it back to the lens, work out here what the deflection angle is, give that deflection angle to the lens and trace it back. So you can always work out where a source would have been, or where the source really is, if you see the lens. But the inverse problem, to take a source and ask yourself, where am I going to see the images, is a more complicated problem. So going from the source plane to the image plane is always easy. Going from the image plane to the source plane, from the image plane to the source plane is easy. From the source plane to the image plane is usually more complicated. And again, we're going to go through this in more detail, but this is just to prepare you for this aspect. And then, because lenses, like the point mass already, it has a large bending mass close in and a small bending angle further away. These bending angles are different everywhere, and so once you have more complicated mass distributions, like a galaxy cluster or a binary system or something like this, then you will find that the bending angle can be different in lots of different places. And that means that these distortions of the sources by the lens can actually be very complicated. So you can have a source here, you have a source which is roughly rectangular, for example, and you can have in lots of different places different bending angles, which means that when you reconstruct the source, you actually would have something that looks quite different from the thing that you see in the sky. The images and the sources can look very different. And again, we will go through this in more detail. This is an important concept which by the end of today you should really understand or work to understand. And that's the concept of caustic curves and critical curves. And the reason for this is, again, we will treat this mathematically later, but the reason for this is that if you consider this transformation of a source into an image because of the lens, that's kind of a remapping. That's kind of a remapping of the sky from unlensed coordinates to lensed coordinates. These mathematical maps can be invertible, they can be non-invertible. You can get complicated structures in them. And these caustics and critical curves basically define the geometry of these mappings. So if the map is invertible, then you have no problem. If the map is not invertible, then you start to see these critical curves, and these critical curves define where you might get interesting phenomena like multiple images, like very elongated or distorted images. And the caustics is the same thing in the source. This is just a placeholder. We will explain all this in detail later on. So here's an example of the calculation. We'll come back to this later. This is a kind of mathematical description of how a point mass changes the sky. So here on the right is a source plane that I've invented. So I just imagine there's a piece of sky which is red except for these various colored round sources. This is what you would see if there were no lens. If you now put a lens in front of the middle here, which behaves like a point mass, the one that I showed you before, then instead this is the sky that you see. All the colored images get very distorted, they get moved around. This green one, for example, turns into two different images. This yellow one turns into two different images. Very distorted. This is the kind of mathematical result that you get from putting a point mass in front of a light, in front of a part of the sky and seeing how it how the gravitational lensing changes. And this white curve here, this is what we call the critical curve. And you see it's kind of an important part of this mathematical mapping. This yellow one, this yellow source, for example, which was quite close to the middle, gets split into two images, one of which is inside and one of which is outside this critical curve. This green one, same story, and things seem to happen close to this critical curve. The sources that are far away basically don't get distorted very much, but once you get close to this area, interesting things can get. And this is a kind of singularity of this mapping, where things get interesting and also complicated. And these things are kind of generic, so if you take a different model, this is not now a point mass, but a kind of simple model for a galaxy, an extended mass distribution, you see very similar behavior. And if you make it very elliptical, then you get even more complicated behavior, where you can now get for the same source, for example, this one here, you can now get 1, 2, 3, 4 different images. This green one, 1, 2, 3, 4, same story. Parts of the sky now where it gets kind of dangerous. The source falls here, its images become very complicated. So again, we will come to all of this later. This is a real lens, this is not a model, this is the real thing. This is a quasar that's sitting right behind the center of the galaxy, and the light of this quasar along 4 different paths is bent back towards us. So the single quasar has 4 different images, and here in the middle is actually the center of the galaxy that's doing all this. So, and you can learn a lot from studying exactly the distances, the configuration of these images, the relative brightnesses, their variations and things like this. So this is what we will talk about tomorrow in strong lens. This is called the Einstein cross. It's one of the most famous quadruple quasar lenses. This object, I'm not sure whether this particular one is, but objects like this do vary in time. So in fact, you get interesting effects that if the quasar has an outburst, for example, then not all these images will show the outburst at the same time. There's a time delay between, so you will see first one of them light up, then the next one, then the next one, then the next one. And by measuring these time delays, you again learn a lot about the structure of the lens and also its way of actually measuring distances in cosmology. Yeah, this is a topic for tomorrow. Nice example of strong lenses. And so the general, the way lensing is usually defined, and the way also the book that I put on the web is defined, is we have these 3 different scenarios in which lensing occurs. 3 regimes, if you like. We have strong lensing, which is the most spectacular. That's when you have these caustic curves and critical curves and complicated phenomena. That's the case where the deflection is large enough that you can get more than one image from the same source. So you really are jumbling up and stretching the sky in a very serious way. So that's why it's called strong lensing. That gives you multiple quasars, for example, like the example I just showed you. Then weak lensing is the opposite. Weak lensing is when you're far away from a gravitational lens or when the lenses are not so strong. You don't make multiple images, but you're just gently distorting the sky, gently pushing images around a little bit, which is something you can actually measure and get a lot of information from, but it's very different from a quasar with lots of different images. So that's why it's really treated in a different way. That's going to be the last day of the course this week. And in between we have microlensing, which is really an application of strong lensing. Microlensing is lensed by a point mass, but now by the point masses are stars in our own galaxy. And the deflections of stars are very, very small, but nonetheless you can see that lensing is going on because everything is moving with respect to each other. You need to have a very good alignment between the lens and the source to give microlensing, but because the stars in the galaxy move, if you wait a few months, actually the lens configuration changes. That's something we can measure and again learn a lot about masses of stars and motions of stars in our own galaxy. So those 3 regimes, I'm going to give you a few examples of each of them now. This is a nice example of strong lensing. These are the yellow things in each of these cases. These are real images from the Sloan survey, I should say. In each of the cases you have a different lens. The yellow things are galaxies at a redshift of 0.2, 0.3, something like this. And the blue things are galaxies which are almost exactly behind them at a redshift of 1 or much further in any case. And instead of looking like normal, simple, small galaxies, as galaxies do, they've been completely deformed by the gravitational lensing effect into these rings and arcs and multiple features. So these cases where you have an almost complete ring, where light is basically getting around the lens from all different sides and making it back towards us, these things are called Einstein rings. And if you can measure such an Einstein ring, it tells you a lot about how much mass there is associated with the lens. It's a very strong way of measuring the strength of a lens very accurately. So this is strong lensing. Here's another example. This is a galaxy cluster. So these were the previous plot were strong lenses where the lenses were individual galaxies. Here the lens is a galaxy cluster, much bigger mass than individual galaxies. And you see that this cluster, again, deforms. You see all these little tangential arcs. If it were dark here, you would see many more images like this. Also these things here. These are all very strongly distorted background galaxies whose light, when it meets the gravitational lens of this big cluster, is really completely changed. And this pattern of tangential alignment around massive objects is a fairly typical thing that you get in strong lenses. There are many strong lensing clusters known like this. In fact, there's now a very large project on the Hubble Space Telescope going on called the Frontier Fields, which is imaging specifically strong lensing clusters to try to learn a lot about the distant galaxies behind it. The reason why this is interesting is that these things, for example, these background galaxies are very strongly magnified by this lens. And so it's like having a telescope in the sky that helps you to understand very distant galaxies. And so this is what we call the gravitational telescope. It's like using the telescope in the sky to help us see even better than we can with telescopes on Earth. So you can do many things with a strong lens if you understand it really well. You can both use it to figure out exactly how much mass there is in this lens. You can try to understand the strength of the lens and therefore see how much dark matter there is in these galaxy clusters, for example. You can also use this gravitational telescope and you can try to look at, for example, this is a famous example here, is one galaxy which is kind of ring-shaped, and there's a total of 7 different images of this galaxy spread around this cluster. And each of these, the fact that you know that these are images of the same galaxy means you can do you can get a lot of information about what the galaxy really looks like intrinsically. And this is, for example, this is 1 arcsecond on the unlensed source, and this is how well you can reconstruct this from space telescope images. So you see that you have this tremendous magnification, which means you can look in much more detail at background galaxies. And then the other thing we talked about briefly is this time delay question, which is a way to do geometry with the universe. Something we will discuss tomorrow. Weak lensing is, as I said, the opposite. It's a more subtle effect. We're talking now about very small deflections and no multiple images, but simply about the effect that if you have a lens in some part of the sky, you have this effect that it kind of pushes away background images very gently, but it doesn't do it to such an extent that it really rips the sky. It simply gently distorts the galaxies. It has a tendency to push things a little bit in these tangential alignments. And so that's the typical pattern that you see, again, much less strongly than I've drawn it there. It's a pattern that you can try to measure, and if you can measure this, then you have a lot of information about the mass distribution between us and the distant universe. So you cannot measure these deflections directly, but you can try to look for this pattern, which is basically based on the gradients of the deflection. I will show you how this is done on Friday. And once you can do these detections, then you can say something about the mass distribution of the large-scale structure between us and distant galaxies. And this is turning into a very important cosmological test of our whole lambda CDM cosmology that tells us how fast structure grows, on what scales, how massive clusters have to be, etc. So applications of weak lensing are the outskirts of galaxy clusters. If this is a galaxy cluster, then the strong lensing effects would be somewhere in here. With weak lensing, you can measure a much larger area because you can measure these more subtle, weaker effects. So you can measure cluster masses out to much larger radii. You can do the same thing for galaxies. And you can also try statistically to measure the power spectrum of the mass distribution. And as you know, the universe is full of not only galaxies, but also full of dark matter. Dark matter doesn't emit light, but it does have gravity. And so this is one very powerful way of measuring the distribution of all the matter, light or dark, and thereby learning something about how the dark matter affects the cosmology. All right. And then microlensing is what we will do on Thursday. So microlensing is strong lensing, but by individual stars. That means that you get image separations not on the order of arc seconds like you do for galaxies, or arc minutes like you do for galaxy clusters, but much smaller, basically milli arc seconds. Much smaller than you would be able to see in a telescope. The telescope typically blurs things by at least a few tenths of an arc second. So two images separated by a milli-arc second are completely invisible. But what you do get is image configurations that change as the stars move with respect to each other. If the source moves or the lens moves, things will change, and that gives you a characteristic variation in the total amount of light that you get from the star. You get these kind of single brightening and symmetric one-time brightening and fading due to one of these microlensing events. And there's been a lot of work in the 90s and the last decade trying to measure this, which is a kind of 1 in a million type of effect. But nonetheless, by now people have collected many hundreds of these events and used them to study the distribution of stars. So that's for Thursday. So here are some applications. There's something called the experiment, which ran in the 90s, which was to try to see how much of this microlensing really happened, and therefore how much of the dark matter in the galaxy halo consisted of star-like objects, compact dark objects. The conclusion is that there's none, so the experiment was a success, but a null detection, if you like. I've been involved in studies to repeat this in nearby other galaxies with similar conclusions. Matches are no longer there. But now this is moved into trying to find planets, for example. This is actually a very powerful way of finding planets around very distant stars, because the planets affect the microlens. And you can also use it as a gravitational microscope. I showed you that strong lenses from clusters are gravitational telescopes. They look at distant galaxies. Here you can actually have a magnification pattern that is smaller than the surface of a star. And so you can scan across the surface of a star and measure, for example, whether the limb is brighter than the center. You can take a spectrum during these various epochs and really look at surface structures on stars being lensed because they're being magnified so tremendously by this microlens. Okay. So that's a kind of overview of the kind of concepts we're going to be dealing with. The rest of today is going to be on the blackboard and lots of formulae, I'm afraid. The idea is that with that you will have, you will be prepared to actually do lensing calculations and understand what the fundamental aspects are and what you can actually do.
I have a general question. May the properties of some objects in the sky be strange because of the existence of a lens or something like that? I mean, if you see something that is very strange and does not fit with with theory, you can recognize that it is produced by a lens.
Sometimes yes, because if you can see the lens, if you can see a bright galaxy nearby, then it makes sense to think that this is affecting the light rays, that it's causing lensing. Sometimes you see strange objects, but there's no obvious lens, and then it becomes a possibility, but not necessarily the right one. One example, for example, is that if you have, if you're looking for very bright objects, supposing that you look for very bright quasars, high redshift bright quasars, then suppose you find 20, then almost always the brightest ones are actually brighter than they should be. And that's because those are lensed, and so that makes them more likely to be found. And so in most cosmological samples, once you go to a high redshift, which is what you need to get efficient lensing, the brightest objects are almost always preferentially affected by lensing. So, and that doesn't necessarily mean that you can see the lens doing or the galaxy doing the lensing, but nonetheless it is an extra scatter, an extra systematic effect that can affect it. So
And okay, I know this effect is very small, but can dark energy produce some kind of lens effect on the light coming from very far away objects?
No, because lensing, as we will see later, lensing, if you have a uniform distribution, it doesn't cause lensing. I mean, it can cause an overall magnification, but it doesn't cause lensing that you can recognize very easily. What dark energy does do is it changes cosmological distances, and that's actually something that with lensing we can try to measure, because it's a kind of geometrical angle thing. We'll come to this on tomorrow, I think. But it's really mostly a probe of matter and dark matter, not so much of dark energy.
Si la masa produce lentes gravitacionales, entonces ¿qué producirá vacío? Voids. What will produce voids?
So I didn't have. So if the question whether vacuum.
Si la masa produce lente gravitacional, ¿qué producirá vacíos?
So if you have an empty region of space
Yeah.
surrounded by masses, then it's like the negative effect. If you have a huge empty region of space, it doesn't do anything. But if you have an overdensity, right, a region of more mass than the average, that produces the kind of lensing that focuses, that I showed you. A region which is underdense, which has less density than the surroundings, produces a divergent effect.
There is a theory that can puede comprobar eso. ¿Hay alguna teoría que pueda probar eso? Que diverja.
So you will never get strong lensing effects from an empty region because the mass contrast is not high enough. But when we come to talk to weak lensing on Friday, then you will see that you are just as sensitive to overdensity as to underdensity. Okay, so we can switch off the computer.
No question.
For now I'm done.
What is the minimum mass that a galaxy has to have to be detectable by a gravitational lens?
Ask me again in 2 hours if you don't know the answer. We're going to come to this. So it's not so much the mass, it's what you need is a minimum surface density of matter. And the surface density is a few thousand solar masses per square parsec.
Thank you.
We will come. Maybe in the second half, but not the next half. Then if
Aprovecho para anunciarles que el profesor y los demás profesores del programa de astronomía vamos a estar en la oficina 6414 disponibles para discutir, para resolver los ejercicios, mañana en la mañana seguramente. Y de modo que si quieren discutir algo más de lo que se ve aquí, bienvenidos en la oficina. You agree, Kun?
Yes.
You will be available.
I don't know what you said, but yes.
You will be available from 7 o'clock tomorrow. No.
Who will be there at 7? We can make an appointment. Okay, so what is can I just ask a social question? What is the custom here? In Leiden, after 45 minutes, the students are all going, oh, I need a break. Are you okay for 90 minutes, or do you need a break?
They are used to 3 hours, so.
That doesn't mean that they like it. What do you want? We continue? Okay, so let's start to put some mathematics on these concepts. So the first thing that we started with was this question of how a light ray is affected by a gravitational field. Right? So here I have a mass m, and I have a particle that I'm launching with speed c along a straight line past the mass, and it's approaching to a distance r. Now this particle, wherever it is, it feels an acceleration towards the mass, right? And the acceleration, when it's far away, will be small and will be mostly directed along its direction of motion. Same thing here in the other direction, but when it's close to the mass, this acceleration will be perpendicular to its motion and will be strongest. So this acceleration is simply given by Newton's acceleration. So that's gm over the distance squared, and the distance squared is r squared plus z squared if I make this the z coordinate along the path, and r is the distance of closest approach. Right? So at any point here, to make this triangle with a z and an r, and then the distance here is r squared plus z squared by pi. Right? Here. Now that's the length of the acceleration. The horizontal components of the acceleration over the full length of the orbit will cancel out, because at this point you're being pulled in this direction, at the opposite point you're being pulled equally hard, or accelerated equally hard in the other direction. But down here, all the effects will add up. The effect is always of the same sign. So in the end we're going to have a net acceleration in the down direction. And the game will be to integrate this acceleration over time, and that will give us the net change in velocity in the vertical direction. And once you have a change in velocity, then you will have moved the orbit of the particle, and you will actually have bent the orbit. Yeah. Maybe you should leave the microphone.
I know it's uncomfortable, but don't worry. Just ask for the microphone.
Yeah.
Estamos asumiendo que la masa no está rotando.
It's just a point mass, in fact. It can be a point mass. It's just a circular symmetry.
Estática.
No rotation. And again, in Newton, it doesn't matter. It can rotate as much as it likes. There's no frame dragging or anything like this. So the acceleration is gm over r squared. The vertical acceleration is this, because I've had to multiply this acceleration by the sine of this angle, which is r over r squared plus x. Right, so at any point, this is the component of acceleration towards the mass that this particle produces. So now we can calculate this integral. dt by dz over c, because z is c times t if the particle is moving at speed c. And this integral I happen to know is 2gm over c squared. Right. It's a very simple integral by if you substitute. Like. So here's the integral of the acceleration in this direction. So this is the velocity in this direction that this particle picks up as it flies past this mass at speed c. And so the bending angle is the change in direction, which is the vertical component divided by the horizontal component. Again, I'm assuming that this angle is very small. And so that's 2gm over c squared r. This should be c. So this is the angle that I showed you in that plot before. Lens. This is what you get here, and you see that it's inversely proportional to the distance that you approach the mass. So the closer you get, the stronger this effect is, as I showed you in the drawing. And now this is where the magic comes in. This is Newton. General relativity means you multiply by a factor of 2. And so the angle is and this is kind of the central result that we're going to use as the basis for everything. This tells you how much mass bends light, and that's all you need. Now, where did this factor of 2 come from? If you if you look at the metric of GR, then you see that there's a gravitational potential here in the time term, but there's also the gravitational potential here in the space term. And it's because these two potentials appear here, that's why you get the doubling of the effect. If you had only a Newtonian system, then there would be no space curvature and this would not be there. So this, again, it's not a mathematical proof, but basically if you follow through the geodesics, the light rays in GR, then you find that each of these terms contributes, and that's why you get this doubling of the bend. So this is in big brackets, because that's not what this course is about, but this is the answer I'm going to give to your question. I hope you're satisfied. Okay, so that's it. That's how strong a gravitational lens is. Now, of course, point masses are very nice, but they're very limited. So what we have in general is more complicated structures. We have galaxies that consist of lots of stars. We have distributed mass distributions. We have maybe binary stars. And so what you really want to do is be able to work with not just one point mass, but with a mass distribution. And so to get to a mass distribution, we basically the same calculation, but now we assume that again we have a light ray that's traveling at speed c, and it passes by a region of space where there's an extra concentration, where there's a lens. And this lens, this part of space we're going to describe in x, y, z coordinates, and in that space there's going to be a mass density rho. So you can think of this as lots and lots of point masses distributed in this part of space, and each of them will try to bend the light according to the point mass formula, and you have a total combined effect of this whole mass distribution. Now, because all these effects are small, they basically add up. It's completely linear. So the simplest way to think of this is to also think of the Newtonian potential phi, which describes this mass distribution, right? With the Poisson equation that relates the potential to the density. And then you can repeat exactly the same calculation that we had there, and you can say that the vertical speed is equal to the integral over time of the acceleration. In fact, now I shouldn't call it vertical, I should call it xy. Yes. The one I'm used to has a magnet, that's why I'm going to drop this more often. Don't laugh too hard. So as a particle moves through this region of extra mass, then it feels an acceleration in the x and the y direction. Let's call this again the z direction along the motion. So we're interested in the reflections in the x and the y direction. The acceleration is simply given by the gradient of the gravitational potential. And so the velocities that get picked up by the light in the x and the y components are equal to the time integrals of these accelerations. We can replace time by z again divided by c, and we can replace the accelerations by the gradients of the potential. And now we can do a trick. We can take the derivatives out of this integral and you see that what counts is basically the integral along the line of sight of your gravitational potential. Like you take the whole lens and you squeeze it along the line of sight, and that tells you how strong these gradients are. And so the bending angle is just like before. It's the transverse speed divided by the horizontal speed, so it's dx over c dy over c, and that's going to be equal to Right, I've just added an extra factor of c, and I'm going to make a definition here that that's and I'm going to put a 2 in there. That's fine. So I'm defining this new thing called the lensing potential, capital phi, which is the integral along the line of sight, so into the sky, of the three-dimensional Newtonian potential. Because in the end, all that matters is the deflections in the horizontal directions, right? Not along the sight, but in the direction of the sky. And for that, we can simply integrate over the third component. And this factor of a half is what people usually put in as a convention. So this is, you see, exactly the same kind of calculation as we've done here. I've taken a light ray, followed it along a straight line, assumed that all the deflections are going to be very small, and simply integrated all the transverse motions, all the transverse perturbations, to get a net transverse velocity, which then translates into a net bending angle, a net change of direction.
This capital P will not depend on C, right? On theta.
It's the projection.
The projection. So
there's
a dependency.
Yeah.
there.
So it doesn't actually matter whether a particular lensing mass is here or here. In the end, all that matters is the projection, and that's true as long as this region is a lot thinner than the full length of the line of sight. So this is what we call the thin lens approximation. And as we will see next, not only the potential you can collapse, but you can also collapse all the mass. In fact, all that matters is the surface mass density of the three-dimensional structure. That's what's coming next. Is that you? Okay.
So if you are not sensitive to the three-dimensional structure of the intervening thing, how can you do this three-dimensional maps of the distribution of mass in these clusters? And
you cannot do the 3 dimensions. You can only do, with lensing, you can only do the 2-dimensional projected mass. Unless you have very elongated structures. If you have one cluster behind another, say a cluster at 0.2 and another cluster at redshift 0.5, then you can try to disentangle the two things by seeing how things that are lensed, which are behind both clusters or only behind one cluster. But if you have a cluster of a certain size, that all you really see is the projected mass distribution in that cluster. That's what. And the reason is that the light rays fly by so fast that they don't actually. They simply feel the cumulative sideways pull, but they don't actually notice very much where exactly it's at. So So this capital phi is what we call the lensing potential, which is really just this two-dimensional object that depends on the sky coordinates and not on the depth. And so we can do some potential theory with this, just like in 3 dimensions. We have the Poisson equation. We can integrate this over the line of sight, and we can get the Poisson equation in 2 dimensions. So if sigma is the surface mass density, the integral of the 3-dimensional density over the line of sight. So then, just like the Poisson equation relates the normal potential to the normal density, in 2 dimensions, this lensing potential is related to the surface mass density. And so let's cancel the factors of 2. Just in 2 dimensions. Yeah.
Is this the Newtonian version?
This is all Newtonian still. The factor of 2 is still coming.
Okay.
But it will be the same. I'm going to put a factor of 2 in here to get the 2. So just like in 3 dimensions, we know how to solve the Poisson equation by taking basically the solution for a delta function density and integrating that over all the point masses in your problem to get a distributed potential. You can do exactly the same thing in 2 dimensions. In 2 dimensions, the delta function mass distribution in projection corresponds to a log R potential, whereas in 3 dimensions I have this. So this is in 2D. This in 3D. And so this gives you the recipe. If I give you a general surface mass distribution of a lens, this gives you the recipe to construct the total lensing potential. So I can write down the formula if you like. But, so this is taking this this delta function and integrating it over a distributed mass distribution. In practice, we almost never calculate potentials this way, but this is nonetheless, this is the full closed form. Like in 3 dimensions, you would do the same, except you would replace this by the rho, by the mass density, and this by the 1 over r, that is the potential due to a single point mass in 3 dimensions. And so if we go back here, we put in the factor of 2 from GR, and we get our lensing equation for a general mass. Is this right? Yep. And so what we will see later is we will take specific examples of mass distributions for which it's easy to calculate the surface mass density and the potential, and we will learn and practice a little bit how this actually causes the gravitational lensing features that we see on
Kun, what is this symbol inside the integral given the lensing potential? Is this the natural logarithm? I'm sorry for the question.
this? Yes.
Yes. The logarithm.
Yeah. Here? Where does it come? That was the question?
You read it fast and I didn't understand it.
So
no problem.
No, so these are the results from potential theory. If you try to find out what's the force field and the potential due to a point mass, in 3 dimensions you have a 1 over r potential. If you do the same thing in 2 dimensions, you would find the log r potential. And it's a solution of the Poisson equation, which
The G Laplacian of green function is minus 4p del not
the G. I'm sorry. Yeah, you're right. Okay, so I made 2 mistakes in one equation. That's pretty good. This G should not be there, and there should be a minus sign.
with minus.
Very good. All right. Is it clear that if I give you a lens, I give you a mass distribution on the sky, at least in principle, you know how to get to the deflection field, This is the flow chart, if you like it, you would have to follow. You have to know the Newtonian potential. You have to integrate the Newtonian potential into the sky to get this lensing potential, and then you take the gradients in the direction of the sky, not into the sky, but in the plane of the sky, to give you the bending angles, give you the gradient. And in fact, if you did this calculation using a point mass potential, you would get exactly the same thing as what I had here before I wrote it. All right. So this was just potential theory. Now we get to the optics part. Maybe for that I should change color. So the lens equation answers the question, if I have me as an observer here, I have some lens somewhere along the line of sight, and I have some distant source. So here's the source, here's the lens, which is usually called D for deflector, deflects the light. And this is the observer here. Then the lens equation tells us what's the relation between the images, between the various positions and the angles. Basically tells you how to solve these kind of ray traces. Right? The potential theory I just told you gives you this deflection angle here, but that doesn't necessarily tell you where you're seeing the source. So to do this, we need to introduce some new coordinates. So let me. So this is the deflector plane, this is the source plane. We're observing a light ray from a certain position in the source plane here, and that light ray we know has been deflected by an angle alpha. That angle alpha we've calculated from potential theory, but at the moment it doesn't matter where we get it from. We simply know that there is this deflection, and we want to know what has this done to my image of the sky. So if the lens had not been there, I would have seen this source in this position. Now the lens is there, which is moving all the light rays around, and instead I'm seeing this source, the light coming from this direction. And so let's also define just an optical axis here, which is the origin, and then we can define the angle beta, which is the angle to the original source position here, and we can define the angle theta, which is the angle to the image that we see. So this is the theta is the image position, and beta is the unlensed source position. And now we can also define some distances in this problem. This is the distance to the deflector. This is the distance from the deflector to the source. And then there's also the total distance here, which is the distance to the source. And so what the lens equation does is it relates these three distances, deflector distance, deflector source distance, and source distance, to the three angles in the problem, which is the unlensed position beta, the lensed image position theta, and the bending angle alpha. So it's really very simple geometry that we do, just a little bit of trigonometry. But once you have the lens equation and the potential theory here, then you've really set all the physics of the problem in a single equation. So we'll.
I'm sorry. How is defined this beta? What is these two lines?
So this is simply a reference line.
Reference.
Just the origin.
Okay.
We will see that in the end all that matters is beta minus theta.
And these angles are not in the same plane, right? They are not in general in the same plane. I mean in space.
No, so in fact the way to do it is to define coordinates in this deflector plane and the source plane, and then so psi, for example, is in the deflector plane, and that's equal to this distance times the angle theta to the deflector. Similarly, coordinates in the source plane are like this. So you can either work in these Cartesian coordinates in these planes, or you can work with the angles. And in the end, we're going to want the angles because that's what we see in this. So now we have to do a little bit of, again, remember that all these angles, I've drawn them quite large, but we're going to assume that all these angles are really, really tiny. So again, sines, angles, and tangents of angles are simply equal to the angles. So that's already what I've assumed. This once again, this very small angle approximation. And so what you see now, if you imagine following a light ray in this direction, let's try to figure out how we get to this position eta here. Well, it's this light ray which ends up at eta first travels to this position psi in the deflector plane, and then it moves back because of the bending angle into this direction, and moves back by an amount which is given by the bending angle times the distance over which it travels. So it's d ds times alpha. Now in fact, it should be a minus. So we always have the convention in these because of the way we've defined the potential theory and taken the positive gradient of the potential. We always have the convention that alpha bends in the opposite direction from the angles of theta positive. So this is simply saying that the displacement in this direction to get to the deflector plane plus the displacement from the deflector to the source plane due to the bending puts us back at the original source. Is this clear? It's not very, it's messy but not complicated. And now what we're going to do is replace these coordinates by the angles so that we get a relationship between the angles and the distances, which is really what we want to be able to work with. So eta we said is dd, is ds.
Just to clarify, this underline is vector.
That means a vector, yes.
It's a vector.
What's the notation you use? A different notation?
Okay.
Overline.
Yes, overline.
I hope this is okay. Otherwise, have I done something right? Let me just check. This doesn't work.
Recuerden la hoja de asistencia, muchachos. Exacto. ¿Dónde está la hoja de asistencia? Por favor, háganla circular. El que la tenga trancada por ahí.
I've done something silly because this is what I have in my notes. Yes, okay. I said it wrong. The way to do this is to take this, to do everything in the source plane. So in the source plane you have the source position without lensing is given by beta times the distance to the source plane. The image position in the source plane is theta times the same distance, and then what we move in the source plane is this DDS times alpha. So that's why it has to look like this. And then here we get so this is the lens equation in the angles involved. Again, these are all vectors in principle. So this shows you that the change in position on the sky between the unlensed and the lensed position is equal to the deflection angle multiplied by this geometrical factor that simply tells you how much distance there is beyond the deflector versus the distance, the full distance.
The last equation, what are the observables? What is observable? What can be observed?
That's a very good question, because in principle, if this were a physics experiment in the lab, you could take away the lens, and that would tell you beta. It would tell you where the source was. And then you can put the lens back in, you can look again, and you can see where the image is, which would give you theta. We don't have that luxury. So in principle, you can only observe complicated combinations of these things. If you have a multiple image lens, for example, then you don't know what beta is, but you know that the two different theta, the two different images that you get, correspond to the same beta. So you can at least say that this term has to be the same for the different images.
That's right.
So you always have a little bit of information less than you would like to have in lensing. That's part of the problem. And that's really because you cannot do the experiment of moving the lens away or making it stronger or turning it or whatever. In weak lensing, you get to see, not even this, but you get to see the gradient.
So the only thing that I can observe there is alpha, isn't it?
Alpha you cannot observe either. Alpha is the deflection angle which depends on how much mass there is in the lens. You may think you know how much mass there is in the lens, but if you cannot see the dark matter, you also don't know that for sure. So, in cases where you have multiple images, where you have Einstein rings, then you can constrain this a lot more. But it's not a very simple, clean physics experiment like.
Are you going to give an example?
I'm going to give examples tomorrow. Okay, so that's the lens equation. And in fact, usually people write this in terms of what's called the scaled deflection angle, which is just this combination here. Because in the end, what this shows is that if I move the source further away and the deflector further away, but keep this ratio constant, I don't actually see any change either in the source position or the image position. So all that really matters is this combination. Okay. Maybe I will stop here because the next thing is actually the answer to somebody's question about how much mass you need in a galaxy to cause this lensing. So we're going to derive this critical surface density that you need. But if I start it now, then I won't finish it before the end of the class.
Okay. So, entonces, nos vemos a las 4 aquí mismo. Okay. ¿Alguna pregunta sobre la dinámica de los cursos? Recuerden, sí, Carolina.
Va a ser como el año pasado que eran con quiz, o cómo va a ser la dinámica de evaluación.
Correcto, tú, como llegaste un poquito más tarde, entonces efectivamente cada día va a haber un test basado en estos ejercicios que nos va a poner todos los días, ¿correcto? Okay. Al final, quienes obtengan pues más de 3 en el curso, pues tienen, como les he dicho, un certificado de aprobación en el mismo. Muy bien, las personas que vienen de afuera, podemos conversar hoy también más tarde para refinar algunos detalles sobre su participación. ¿Ok? A las 4, muchachos, muy en punto. Gracias.